Welcome, students. Today we are going to discuss that second part of the potential energy. Okay, in the last class we have discussed the what is potential energy. Okay, how can it be related to that conservative force and all. And in today's class, basically we are going to discuss the potential energy only, but we are going to have some numerical applications on it. Okay. So as you know, it is from work energy power chapter only. And my name is Amarnath, and today will be the day 2. Okay. So let us discuss a question first. Okay. So the question is the potential energy of a particle in a space is given by x square plus y square. So find the force associated with this potential energy. Okay. So what does it mean here? Actually, they are saying that potential energy function is just x square plus y square. Means at different coordinate, the potential energy will be different. Okay. So from that, I can calculate that on force also. What force is there? Okay. If it is a gravitational potential energy, so I can calculate the gravitational force. If it is a electrostatic potential energy, okay, whatever it is, I can calculate the electrostatic force. Okay. Anyway, so what is given here? Given that potential energy symbol, normally we take U only. It is given as x square plus y square. Okay. So it's given. But I need the force. Okay. So we know. So I have already written this. Okay. In the last class. So F equal to what? Minus du by dr. Okay. So negative gradient of potential energy is called conservative force. Okay. That part also I have written. Now also I can write it. Okay. Negative gradient of potential energy is called conservative force. Okay. You should learn it. But force is a vector quantity. So if I need fx, means x component of the force, so it will be what? Minus dx of u. Okay. And similarly, if I want fy, so it will be ddy of u. So here actually, if you now differentiate it, it is ddx of x square plus y square. So as you know that differentiation of x square is what? Differentiation of x square is 2x only. Okay. 2 is the power. Okay. It goes to the place of coefficient and power reduced by 1. And this part will be 0 only. Okay. Because we are differentiating partially with x. So while we are not differentiating with y. Okay. So it will be 0 only. It will behave like a constant here. So it will be minus 2x only. Okay. That is the x component of force. Okay. If the potential energy is like this. But we need the Fy component also, na? So, and Fy I can calculate with the same logic only, okay? du by dy, okay? So it means dy of, so this time actually x part will be constant, okay? So it will be what? Minus, this part will be constant and this will be 2y only. So it means you can say that Fy will be minus 2y. And fx was eaten, okay? Minus 2x. So therefore, the force will be what? Force is a vector quantity, na? So minus 2x I cap means x component, minus 2y z cap, okay? So this is the final, you can say that answer, okay? Force. So they are asking actually force only, okay? Find the force associated with this. So we do not require to calculate dz, that one du upon dz, okay? Because there is no z component of z part of the energy here, okay? Na? So we do not require, okay? If you differentiate also, you are going to get 0 only. So this is the, finally you can say that this is nothing but the answer, okay? So, let me try one more question of this kind, okay? Say this is one question. Find the potential energy of the given force F is equal minus 2x I cap minus 2y j cap, okay? You can say that it is the reverse process of that the previous question, okay? You can say like this only. So let us try it, okay? So here, given that this time force is given, okay? F equal to minus 2x I cap minus 2y j cap, okay? So, but we know that F equal to what? F equal to minus du upon dr. But if I write x, so it will be fx, okay? So from that you can see du will be minus fx dx only. But we require actually not differentiate potential energy, okay? A small differentiate potential energy. We do not require. Du means small gap in potential energy. But we need a huge gap. No? So integration of du, you can write that is a del u, okay, in future. So here fx is this much, okay? This is fx. So it is nothing but minus 2x and dx, okay? So here actually now one point is not given initial conditions, but we are assuming like that, okay? Say at x equal to 0, potential energy is 0. Remember, it is just assumption only, okay? That is actually not mentioned in the question, okay? If not mentioned, we will assume like that, okay? In some cases, actually, at x equal to infinity, potential energy is taken to be 0. Most of the cases, it is assumed like that only. But here actually, in this situation, we are assuming like that, okay? So when x is 0 means, or y is also 0, it means when the particle is at origin, we can say that potential energy is 0, okay? It's supposed to be actually mentioned in the question, but it is not mentioned. So it is x, when it is x, potential energy is u, okay? So it will be nothing but, you can say it ux also, okay? Means potential energy at that x part of the potential energy, okay? So you see this is a minus minus, it will plus only, and 2 will be coming out. So integration of x dx, you already know it is x square by 2 only, okay? And limit is from 0 to x. So it is simply ux is nothing but x square only, okay? So exactly that way we can even say that for the fy part also, fy is minus du by dy, okay? So it means du equal to minus fy dy. So integration of du is minus, fy is minus 2y, okay? So it is minus 2y dy. Similarly, at y equal to 0, I am taking potential energy 0. At y equal to y, potential energy u, okay? So it will be u is equal, that minus minus, it will be plus only. So 2 is coming out. Y square dy integration is similarly y dy integration is y square by 2 only. So y square by 2, 2 got cancelled. So u equal to y square. You can say it is the y part of that one, okay, potential energy. So what I want the potential energy, means total potential energy, okay? So therefore total potential energy is nothing but it is x part and the y part. Remember, you don't put by mistake I cap J cap. Okay, don't put, because potential energy is a scalar quantity. It may have some component, but say X part, I am saying it is the X part. Okay, if the particle goes along X axis, how the potential energy changes. This is nothing but this. Okay, but remember, potential energy is scalar quantity. So don't put I cap J cap. Okay, it will be a big mistake actually. Hmm. This is the final answer. Okay. It will be x square plus y square. This will be the final answer. So we can similarly we can try some more. So this one is a question. Okay, find the expression of potential energy U for the conservative force in a, that force is given like this. Okay, y z I cap, x z j cap, x y k cap. Okay, consider the potential energy at point. Okay, that is given. You see, I have already told you, na, that in the previous question, I have assumed at x equal to 0, y equal to 0, the potential energy to be 0. But in this question, they are saying that you assume potential energy 0, but not at x equal to 0, y equal to 0, but at x equal to 2, y equal to 2, and z equal to 2. Okay, that is given. So I have to take in the limit. Okay, that way I have to take. Okay. So how can I solve it? You say. Similarly, okay. Given that force equal to, given that force is equal y z I cap x z j cap x y k cap. It is given in the question. Okay, so I have to calculate the potential energy. Again, I know that potential energy is what?
समझ नहीं
Directly also I can this time I can write it. Okay, directly also let me write it. U is equal minus integration of fx dx minus integration of fy dy minus integration of fz dz. Because you know that this part is nothing but z part of the potential energy. This is nothing but the y part of the potential energy. This is nothing but the x part of the potential energy. Na? We have already discussed all these things. But remember, this time actually what they are saying, this is also actually integration. Okay. So what they're saying, when the point is 2, 2, 2, say x lower limit is 2, y lower limit is 2, z lower limit also 2, then the potential energy they are saying that it should be 2. And when it is say z, okay, when it is say y, when it is say x, then the potential energy is u. Okay, it means upper limit here it will be u. U. So the left part is what? That is u only. You see, if it is not 2, 2, 2, say it is 2, 2, 3, then this part will be 3, okay? Nothing else. So accordingly, we have to correct it, okay? So u is equal, what is fx here? Fx is nothing but yz, okay? Okay, just a minute, huh? Here actually fx is nothing but yz. So it will be, y is also constant, because the x is variable in this first part. So you can put minus y, actually we should put y z dx, okay? But you know that here only x is variable, so yz should be treated as constant only, okay? That is important. So here yz will be going out of the integration. It will be yz. So integration of dx is x only, okay? Yeah, okay, let me put once more, okay? So it will be 2x minus, here fy is what? xz. So it means xz will be coming out, only y will be left, dy. So limit is 2 to y minus fz here xy. So xy again it will be constant only because I am integrating with respect to that z only. But limit is 2 to z. Okay. So potential energy will be what? You see, that is the interesting answer you are going to get. Yz. This part actually it is x. Okay. But I have to put the, if the lower limit was 0, then obviously answer is xyz only. Okay. For the first part. Second part also xyz. Third part also xyz. But they have given a limit. Na? So that is why it will be a little bit different. Okay. So yz. X minus 2 minus xz, integration of dy is what? It will be y minus 2, okay? And it is xy, and it will be z minus 2, okay? So you can keep it like that only, or consider this is the answer only, okay? Nothing else. But if you want, you can just little bit, you can simplify little bit. That can also be treated as answer only, no issue. But if you want, you can little bit simplify it. How? U is equal to, you see, here you are going to get xyz, here also you are going to get xyz, here also you are going to get xyz. It means you are going to get 3 times xyz, okay? And here you are going to get plus 2yz, here 2xz and 2xy, okay? So if you take 2 common, it will be xy, yz, zx, okay? So little bit simplified form, okay, nothing else. So that can be treated as a final answer.
Yes, sir.
Okay, let us try one more question. Okay, this time I am going to give you some time. Okay, you please try this. Okay, this question is from a famous book, actually, H.C. Verma. Okay, Concept of Physics. So the negative of work done by the conservative forces on a system equals to the change in. Okay, so out of the 4 options, which option will be correct? Okay, see, we know that F equal to minus du by dr. Okay, so du equal to what? Minus F dot dr. Force is vector, displacement is vector, so obviously it will be a dot product only. But if I calculate del u, so I have to integrate it. And you know that this is nothing but the work done. Integration of F dot dr is work done. We have already discussed in the very beginning. And as it is potential energy, so force must be a conservative force. Okay, it should not be like friction. It should not be like a viscous force. Okay, it is like gravitational force, is the spring force, electrostatic force, like that. Okay, so it means work done by conservative force is always equal to change in negative of change in potential energy. So out of the 4 options, total energy is wrong, kinetic energy is wrong, potential energy is correct. So this is the correct answer. Okay. Okay. Now, general study of the potential energy curve. Okay. So between, say, 2 particles. Okay, this is the graph. Actually, you should please try to remember. Okay, this is the potential energy graph between 2 particles in space. It may be 2 atoms. Okay, it may be 2 any other particles, or even it may be 2 planets in space. Okay, like that. So graph, that graph will be na little bit. I'm going to draw this graph. You also please try to draw the graph. Okay, the graph will be this only, okay? Basically, this is the, you can say that this is the uh, potential energy graph between two, say, atoms. You can say this is the potential energy and this is the, that one, okay? Separation between the two atoms, okay? You see, say this is your scale, okay? Say this is the scale. Anything. It may be a pencil, it may be the roller, okay? Anything. So if you think of any two atom, okay? Any two atom nearby, okay? So this is the potential energy graph. If you that sorry, this is not R. Sorry. This is not R. This will be R, okay? This is the origin. This is the origin. So when you bring them closer, okay, then also potential energy increases. And when you bring them away from a particular separation, then also potential energy increases. You see, if you bend one scale, so if you release it, they go back to the original configuration. It means when you bend it, the two atoms separation becomes increases, okay? That increase. And reverse also, okay? In the that was inner curve, the separation between two atoms goes decreasing, okay? But they don't like, okay? They don't want to increase their separation from the equilibrium point, and they don't want to decrease their separation also from the equilibrium point, okay? So that is why, that is the elasticity actually, okay? That is why it goes back, okay? So that particular position, okay, that is the minimum potential energy, and this separation is called the equilibrium separation. Say this is the separation, okay, equilibrium. If you want to increase it, then also potential energy goes on increasing, and if you want to decrease it, then also potential energy goes on increasing, okay? You see here actually R is going on increasing, so potential energy goes on increasing. Here actually you see potential separation going on decreasing, okay? Say one particle is here. Say this particle's name is A, this particle's name is B. And here say this is the A particle, say it is fixed. When the B particle is here, means in the natural equilibrium, say normally they are like that, okay? Say 1 micrometer. So it means their potential energy is minimum. When you push them closer, means one A particle is here in the same level only, but B is coming closer, so potential energy increases. Okay? Similarly, if you move them away, so A particle is here only, B particle will be moving away, so then also potential energy goes on increasing. Okay, so please try to. This is a very interesting or very popular. Okay, you can say potential energy graph which will be used several times in your preparation. Okay, so that is that. Try to understand it. Okay, try to understand, and I'm going to give you some that one also. You see here at this point, there is potential energy 0. See, this is origin, so this is the potential energy 0. Here potential energy is positive. Here potential energy is minimum. And remember, when potential energy is minimum, everyone wants to be at the minimum energy state, so where potential energy is minimum, that situation is called equilibrium situation. Okay. And again, if you separate the separation, when they goes up to infinity, infinity means they dissociated. Okay, it means you can say that the scale is broken, the pencil is broken. Okay, like that. Say two papers. Okay, you have torn it out. Okay, means you have separated up to infinity. Then also potential energy will become 0. You see, it is going from negative. It is going on increasing, and when it goes to infinity, then it touches the 0 axis. Okay, so you can say that when it goes to infinity, then also potential energy is 0. So you please note it down, this graph properly. So in general, we can say that the potential energy graph is, remember, the potential energy graph is between two molecules, okay, yeah, in a lattice, okay, solid. You can say it is like that, okay, it is like that. So you know that at this point the slope is 0. Slope is 0. Okay, slope means that is du by dr is 0. So as du by dr is 0, so force is 0. And as force is 0, so it means it is called equilibrium. Okay, force is 0 means it is called equilibrium. And again, there are 3 types of equilibrium. I have already told you. Here also it will be required. Okay, I'll explain. There are 3 types of. One is unstable equilibrium. stable equilibrium and neutral equilibrium. Okay, that is actually energy minimum, na? So that is a stable equilibrium. Okay, I'll give all these things. Okay, I'll give all these things. You just write simply equilibrium only. Okay, F0 means equilibrium, or when F is 0, it means slope is 0. You see, if the graph is like this, now if the graph is like this, so here also one equilibrium I can get. Okay, but that is called unstable equilibrium, because here it is energy maximum. You see, energy is decreasing, 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 and here it is minimum. Then it is going up maximum, 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 increasing, and here they are getting the maximum point. Okay, energy maximum means unstable equilibrium. Okay, very excited. Energy minimum means ideal, means that stable equilibrium. Okay, you can say. You can feel also like that. Okay. I'll explain all these things. Proper notes, no need to worry about it. See, say the potential energy graph is like this. Okay. So potential energy is going on increasing to a maximum point. Okay. Here energy is maximum. But force is 0. You see, slope is 0 means force is 0. So force is 0 means it is equilibrium. But energy is maximum. Here slope is 0 means force is 0. But energy is minimum. So it is stable equilibrium. Stable. Okay. And here again slope is 0. Force is 0, but it is called the neutral equilibrium, because you see here also potential energy and here also potential energy, everywhere potential energy is same only, potential energy constant. Here actually you see potential energy goes increasing, goes on increasing in both the sides. Here you see potential energy goes on decreasing, goes on decreasing on both the sides. Okay, I have already given you an example. Na? Say one bowl is there like this. Okay, say this is the marble. So it is at the stable equilibrium. If you little bit displace it, it will start oscillating about that point only. But if the same bowl is like this, if you keep the marble here, that is unstable equilibrium. Energy maximum, force is 0, but if you slightly displace it, it moves away. It will not oscillate, okay? It will move away. That is unstable. And if it is a plate, horizontal plate, so if you put the marble here, it will be in neutral equilibrium, because if you move it to this point, wherever you release, it will stay there only. So that is a sign of neutral equilibrium. Okay. So that is stable equilibrium. That is unstable equilibrium. Unstable. That is neutral equilibrium. But remember, everywhere force is 0. Everywhere force is 0. Everywhere force is 0. But remember, everywhere du by dx is 0. Du by dr is 0. Because force is 0, na? Means slope is 0. Du by dr is 0. Here also, du by dr is 0. But at this condition, u is minimum. U is minimum. At this condition, u equal to u max. And at this condition, u equal to constant. I have given the notes in the previous previous class only. But okay, no problem. You please write it once more, okay? As much as you write, it will be okay for you only. Okay, it will be practice. Now, let me analyze this once more. Okay, I have already told you the main thing. Okay, so if F equal to minus du by dr be the force acting on the particle at equilibrium, obviously the net force on it is 0. Okay, as the force is 0, it means du by dr is 0. Okay, that is the slope. I have already told you. Okay, no need to copy. Okay, you can write your own way also, no issue. Okay, it is not required that everything should be put line by line. Okay, you should write in your own way. Force zero means equilibrium. Okay, and one more thing, force zero means translational equilibrium. Torque zero means rotational equilibrium. Say your fan is just not accelerating. Okay, it is a rotational equilibrium, we can say. And the translational equilibrium means, say, one object is lying on the table horizontally. Okay, it is not moving and not accelerating linearly. No? Anyway, so what is stable equilibrium? I already told you. Remember that a new point you are going to get here. Okay, first of all, potential energy. Okay, that at stable equilibrium, the potential energy graph should be like this. Okay, means it should gradually decreases, then goes on increasing. Okay, and it is called a concave upward. Okay, concave upward. This graph is called concave upward. Actually, in any concave upward graph, double differentiation is always positive actually, because slope goes on increasing. You see d2 u dx2. What does it mean? It means actually dx by du by dx. Okay, means differentiation of the slope. You see here actually slope is increasing. You see now slope is this, then slope is this. Okay, slope is going on increasing. So increases, it means slopes differentiation will be positive only. So that is why. Okay, you should remember it. Okay, you please put these 2 points. Okay, for stable equilibrium. This point already you have already put. You put this point also. Okay, d2x dx2 is positive, or you can say that slope increases. If you want to write, you can say that slope increases, or you can write graph concave upward. This is called concave downward. Okay, so what I am writing, it is concave upward. Okay, graph is concave upward. Okay, you please write down this thing. So similarly, we can discuss the unstable equilibrium also. Okay, for the unstable equilibrium, again you have to write the second point. Okay, force is zero, so it means du upon dx is zero only, but the double differentiation is negative. Okay, because the graph will be like this. Concave graph is increasing, then decreasing, but it is concave downward graph. Okay, it is called concave downward. You can say the slope is decreasing. Okay, slope decreases. You please write down. This is slope decreases. Here the slope is zero only. Slope is negative like this. Please copy all these things properly. Actually, now the last part actually, that is neutral equilibrium. Okay. That is already I have written. Okay. In neutral equilibrium, what it will be? It will be force is zero, energy is constant. Okay. Energy is constant. So this one is a question. Okay. A particle which is constrained to move along x-axis, say a particle is moving along x-axis only, like a spring. Okay, say a spring, this is the fixed wall and one mass is connected with the spring and pulled, so it will be ready to move along x-axis only. So is subjected to a force in the same direction which varies with distance x, and particle from origin fx, that force is given like this only. Okay, f equal to minus kx plus ax cube, where k and a are positive constants, and for x is greater than 0. Okay, means for the positive quadrant, the fundamental form of the potential energy Ux of the particle is. Okay. So in actually you see in normal cases, the potential energy function between two particles, okay, that subatomic particles on a lattice, okay, it is given by this only, okay, this graph only. But here actually it is they are giving some special case, okay. Force is this minus kx plus ax cube, okay, that is special. So from that actually we have to calculate that one also. Potential energy expression, and from that expression only we can draw the graph. But one more way I can give you, you can see here force, where the force will be zero. You see force is zero, okay, force is zero means what? 0 equal to minus kx plus ax cube, okay. So what does it mean? It mean ax cube equal to kx, okay. So from that I can say that one x is 0, okay. If you solve it, and then you can find ax square equal to k. It means x square equal to k by a. So it means x equal to plus minus k by a, okay. So there are 3 points where force will be 0, okay. What are the 3 points? One is x equal to 0. So here see x equal to 0, force is 0. Here you see x equal to 0. Acha, 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 acha. Here actually this is the force expression only, na? So at x equal to 0, slope should be 0. You see force equal to what? Force equal to nothing but the du by dx, na? Here I have taken force 0. This is the expression of force only, F equal to minus kx plus ax cube, okay? So force is 0, means du force 0, where x equal to 0, x equal to plus k by a. We do not require x equal to minus k by a because we don't have that negative quadrant graph, na? So it means x equal to 0, or you can say that du by dx equal to 0, where x equal to 0 and k by a. Okay, these are the 2 points. So now you see this graph has no, this is wrong only because it has slope, na? It has some slope, okay. This graph is also wrong only, okay. This is also having some slope only, okay. And you can see this graph, okay. Out of these two, this is also having 0 slope, this is also having 0 slope, and this is also maybe a positive value of k by a, and this is also maybe a positive value of k upon that. Out of these two, which graph will be correct? Okay, what is the difference? It is saying that this graph saying that when x is infinity, potential energy becomes 0. Are you getting my point? When x is infinity, the potential energy becomes 0, okay. But here actually it is not like that. Where x is infinity, potential energy goes on to some ekdam negative infinite value, okay. So I think for that now I have to break this, okay, no other way. I thought that without breaking it I can prove it, but anyway, let me prove it. Dual line, okay, it will take only 2 minutes. F equal to minus kx plus ax cube. So we can put it as du by dx, okay. So it will be du by, it will be actually minus du by dx, okay. So it will be kx dx, and it will be minus ax cube dx, okay. So if you integrate it, it will be what? X square by 2, and if you integrate it, it will be what? It will be x to the power 4 by 4 only, okay. So it will be potential energy. But now you can see here, when x is infinity, potential energy is not zero actually, okay? So it means D option is the correct. Here you can see, here x is infinity, you know, at infinity, potential energy must be zero. But here you can see, if you put x infinity, so potential energy, okay, just a minute. When potential x is infinity, potential energy is zero only, okay? This will be same, na? K and A are positive constant only, okay? Value is, but if it is x is infinity, so this become again infinity. This also will become again infinity, okay? So you will be zero. So this is correct, okay? This is the correct answer. But because that D option is saying that at x equal to infinity, the potential energy will be negative. But from this graph, I am not getting this. Na? From this graph, I am not getting this. So finally, option will be U option correct. Okay. At x equal to 0, slope is 0. At x equal to some positive value, which is k by a, slope is 0. And at infinity, potential energy is 0. Okay, this is the final answer. Anyway, on that note, I am going to wind up today's class. Okay, I am having one more class actually. So in the next class, I am going to do again some questions. Okay, tomorrow, if possible, I am going to take all the questions. Okay.